You ever stop and think about that massive, invisible world running just beneath our feet? It's this hidden network that's working, 24/7 to keep our cities clean, keep them safe. Today, we're going to dive into one of its most critical and honestly surprisingly tricky components.
I mean, it's a pretty serious question when you think about it, right? Every single day, we generate millions of gallons of wastewater, and all of that has to go somewhere. So, what is the one crucial piece of engineering that's preventing a total, absolute disaster?
And here it is. The answer is the wet well. Now, it's not glamorous, not at all, but it is so essential. And in the next few minutes, we're going to pull back that manhole cover and see exactly how this hidden hero gets the job done.
The easiest way to think about this is to picture a giant industrial-strength sump pump, but for an entire city. Its job is pretty straightforward, but the stakes, they couldn't be higher.
So what is it exactly? Well, here's the book definition. It's basically an underground collection pit. All the wastewater from homes and businesses flows into it using gravity. And then, once it gets full enough, these powerful pumps kick on and shoot it all uphill to a treatment plant. It sounds really simple, but as we're about to see, managing that process, well, it's a real balancing act. So the first big challenge, it's the pumps themselves. These things are powerful, they're expensive, and if you don't run them the right way, they will break. It's all about finding that perfect, tricky rhythm. The number one enemy here is something called short cycling. Just imagine flicking a light switch on and off, over and over and over again. You know you're going to wear it out, right? Well, the exact same thing happens to these huge pumps. It causes them to overheat and just fail way too early. So here's how the operators deal with this. They tweak what's called the level differential. All that means is the distance between the water level that turns the pump on versus the level that turns it off. See, a narrow gap means the pump is starting and stopping constantly. That's a lot of wear. But a wider gap, that means fewer starts and longer, much healthier runtimes for that motor. It's all about finding that sweet spot. But here's the thing. It's not just about mechanical problems. If you let that wastewater sit for too long just to protect the pumps, you end up creating a whole new, nasty set of chemical and biological issues. So what do you think actually happens? Because when wastewater goes stale, it's not just stinky, it becomes actively destructive. It enters the state called septicity. And you can see the whole awful chain reaction right here. First, the water loses all its oxygen. Then, these specific bacteria that love that environment take over, and they start producing hydrogen sulfide gas. Yep, that's the source of that famous rotten egg smell. But what's way worse than the smell is that the gas turns into sulfuric acid, which literally dissolves the concrete infrastructure from the inside out. No joke. So operators absolutely cannot just let the water sit there. What they do is they use a special pump down cycle. This periodically drains the wet well as low as it can possibly go. It flushes out all that stale water, scours the walls, and stops that toxic chain reaction before it can even get started. Pretty clever. Okay, so we've got the chemistry handled, but now we have the most, let's say, physical problem of all, clogs. And just like the drain in your kitchen, if this system gets clogged, it is a massive, massive problem. Luckily, engineers have a really smart solution for this. The main culprits are things that should never, ever be flushed. These so-called flushable wipes, they're a huge problem. That, plus things like rags and grease. They just don't break down. Instead, they twist together down there and form these giant destructive clumps that people call rag balls, and they can completely choke a pump. So how do you make sure the system never fails? Redundancy. It's all about redundancy. Most stations use what's called a duplex, or two-pump system. You've got one lead pump, that's the workhorse, doing the daily grind. The other is the lag pump. It's the backup. It only kicks on during really high flows, like in a big storm, or if the lead pump breaks. And here's the genius part. They swap roles, usually every day, to make sure they both wear down at the exact same even rate. This quote really just says it all, doesn't it? It's not just about having a spare part sitting around. It's a living, dynamic system that's designed for balanced wear and for total fail-safe backup. It really is the ultimate backup plan to stop a catastrophe. All right, for our last piece of this puzzle, let's get a little technical. Let's look at the physics that governs this whole operation, because understanding this is what really separates the pros from the rookies. So let's set up a scenario. You got a pump, and the spec sheet on the box says it can move 500 gallons per minute. But
And this is a big but. That performance is only rated under very specific conditions. In this case, against 30 feet of something called total dynamic head. Just think of that as the total resistance the pump has to fight against.
But out in the real world, things are different. Today, for whatever reason, maybe there's a valve that's partly closed way down the line. The actual resistance in the system is higher. It's 40 feet of head, not the 30 feet from the spec sheet.
So here is the key question. The pump is working harder now. It's fighting against more pressure. What do you think happens? Is it going to move more water, less water, or the same amount? And the answer, which might seem a little backwards at first, is less water. It all comes down to a really simple principle. Head and flow are opposites. They have an inverse relationship. As the pressure, the head, goes up, the pump's flow rate goes down. So our pump is actually moving way less than its 500 GPM rating.
And that right there is the bottom line. It's a fundamental law of physics for these systems. More resistance always means less flow. If an operator doesn't get that, they might look at their screen and think everything's fine, when in reality, the system is falling behind, and they're risking an overflow. It's that critical. So when you zoom all the way back out, you start to see it's not just one thing. It's the careful management of pump cycles, it's the smart prevention of that nasty chemistry, and it's a deep understanding of physics, all working together. All these little details are what protect our environment and our health every single day.
The wet well is just one piece of this giant, hidden puzzle. It really makes you wonder, though, doesn't it? What other invisible systems are humming away right under our noses, just quietly keeping our world running?